Sometimes in physics, it is said that the number of particles in a system could be 0, 1, 2, and many. In this course, when we worked with an object, whether we were considering the trajectory of the object and determining the object's velocity and position, or whether we were determining something about the forces acting on that object we treated as a single point particle. However, real macroscopic objects that we interact with in the everyday world are not point particles. They are made of Avogadro's number of particles. And keeping track of the trajectory of every particle that makes up an object would be very tedious. So if there were some way we could find a single point, in other words, a single coordinate, x and y, that somehow describes the object's average trajectory, then we would be able to get around having to perform Avogadro's number of calculations. And this point is going to be known as the center of mass. The center of mass of an object or the center of mass of a system of particles is a single point. In other words, it has coordinates x and y, and this point moves as though all of the system's mass is concentrated at the center of mass, and all external forces that are applied to that object made up of many particles are all applied at that center of mass. Now, if a body is symmetric, in other words, if one half of an object is a mirror image of the other half, then the center of mass will lie on an axis of symmetry. We do not always need to do a calculation to determine an object's center of mass. Sometimes we could just reason it out. Here are 4 examples of objects. There are 3 2D objects. We have a rectangle, a circle, and a hexagon, and we have a cylinder. And I could reason that if one half of an object is a mirror image of the other half, then the center of mass will be somewhere on that axis of symmetry. Let us first look at the screen hexagon. I could imagine that if I were to draw a line diagonally down and to the right through the center of that hexagon, I would get something that looks like this. Now, if we were to fold the hexagon along this line, the upper right side of the hexagon would perfectly cover the lower left side of the hexagon. Therefore, I could infer that this diagonal line through the hexagon is going to be an axis of symmetry, and the center of mass of this hexagon should lie somewhere along this dashed line. If we look at the black rectangle on the far left, I could imagine drawing a vertical line straight down through the center of this rectangle, and if I were to fold the rectangle along this vertical dashed line, then the left side of the rectangle would perfectly cover the right side of the rectangle. Therefore, the center of mass of the rectangle must lie somewhere along this vertical dashed line. Separately, if I were to draw a horizontal line through the center of this rectangle, I recognize that the top half of the rectangle could be folded and perfectly cover the bottom half of the rectangle. Therefore, I infer that the center of mass of this rectangle should also lie along this horizontal dashed line. Now, by looking at this rectangle, there is only one point that contains both the vertical dashed line and the horizontal dashed line, and that point is the center of the rectangle. So I could reason that the center of mass of this rectangle should be located right here at the center of the rectangle. If you think about a circle contains an infinite number of possible lines that you could draw where one side of the circle is a mirror image of the other. That would be any diameter of the circle. You could have a horizontal diameter of the circle, or a vertical diameter of the circle, or a diameter of the circle at any angle you want. As long as it passes through the center of the circle, that will be a diameter of the circle. That will be a line where one half of the circle is a perfect mirror image of the other half. And all of these diameters do intersect at the center of the circle. And because of that, I could infer that the center of mass of the circle is located at the center of the circle itself. Now, if I look at a 3D shape, This idea still holds. A cylinder is a nice symmetric object, and one axis of symmetry in a cylinder is down through the center. So I could infer that the center of mass of the cylinder should lie somewhere along this dashed line. And indeed, the center of mass of all of these objects are all located where one side of the object is a perfect mirror image of the other side of the object. So, for finding the location of the center of mass of an object, we could often just reason out the location of the center of mass if the object is a nice regular shape, like a rectangle or a circle. But what if we have an irregularly shaped object? Or what if we have a system of many objects that are separated? Can we still talk about the center of mass of many objects? And the answer to that is yes. When we are finding the center of mass, we are essentially trying to find what are the x and y coordinates of the center of mass of the object. And to find the coordinates of the center of mass, you're going to need to find the x coordinate for the center of mass and the y coordinate for the center of mass separately. The x coordinate for the center of mass is given by this equation, and the y coordinate for the center of mass is given by a very similarly looking equation where we just replace all the x's with y's. Here I am thinking that an object consists of some number of particles, and we'll label those particles particle 1, particle 2, particle 3, and so on for however many particles we have that makes up our object or our system of objects. Particle 1 will have mass m1 and have x coordinate x1. Particle 2 will have mass 2 and x coordinate x2. Particle 3 will have mass m3 and x coordinate x3, and so on. Similarly, particle 1 will have y coordinate y1, particle 2 will have y coordinate y2, and so on. So if we have a system of particles that are not a simple arrangement like a square or a circle, we could always fall back on this equation for finding the x and the y coordinates for the center of mass of some number of particles. Now, the center of mass does not need to physically reside in any objects. If I consider the Petronas Towers, two of the largest towers in the world in Malaysia, I could approximate them as two cylinders, and by symmetry, I could reason that the center of mass of Tower 1 should be right at the center of Tower 1 because I'm treating Tower 1 as a cylinder, and the center of mass of Tower 2 should be pretty close to the central axis of Tower 2 because, again, I'm treating these towers as a cylinder. Now, if I ask, what is the center of mass if these two towers were to be replaced with point particles located at their center of mass? Well, the center of mass of the system of two towers will be located somewhere between them, so right about here. In this example, we see that the center of mass of a system of objects does not need to physically reside in any of those objects to still be a valid concept. The Earth and the Moon have an average separation of 3.9 times 10 to the 8 meters. We decided to place the center of the Earth at the origin, and we are asked in this coordinate system to find where is the location of the center of mass of the Earth-Moon system. So that implies if I say the center of the Earth is located at coordinate 0, 0, then the Moon will be located at coordinate 3.9 times 10 to the 8, 0. To find the x-coordinate of the center of mass for the Earth-Moon system, I would say the x-coordinate for the center of mass is going to be the x-coordinate for the Earth times the mass of the Earth, plus the x-coordinate for the Moon times the mass of the Moon, divided by the total mass of all the objects involved, mass of the Earth plus mass of the Moon. Now, at this point, we have the x-coordinate for the center of the Earth and the Moon. We are given their masses, so we just need to plug in numbers and solve this on our calculator. So I would write the x-coordinate for the center of mass of the Earth-Moon system is going to be 0 times 6 times 10 to the 24 plus 3.9 times 10 to the 8 times the mass of the moon, which is 7 times 10 to the 22. And the total mass of the Earth and the moon is 6 times 10 to the 24 plus 7 times 10 to the 22. Now I just have to solve this on a calculator. Be careful of exponents, be careful of order of operations. Make sure you add these two terms together before doing your division. And when you do that, you find the x-coordinate for the center of the mass, xcm, is going to be 4.5 times 10 to the 6 meters. So what that means is if I place the Earth at the origin, the center of mass of the Earth-Moon system is going to be about 4,500 kilometers away from the center of the Earth. So the center of mass of the Earth-Moon system is going to be somewhere in the Earth's mantle. Now, similarly, I could look at this problem and right away tell you what the y-coordinate of the center of mass of the Earth-Moon system are. I chose to set both the Earth and the Moon on the x-axis. They both have a y-coordinate of 0. So I could see right away that the y-coordinate for the center of mass, based on how I drew this problem, is going to be 0. Specifically, if I wanted to solve for the y-coordinate for the center of mass, I would just have to change these x's into y's. So I would say the y-coordinate for the center mass is the y-coordinate of the Earth plus the y-coordinate of the Moon. The y-coordinate of the Earth is 0. The y-coordinate of the Moon is going to be 0. And then I get 0 plus 0 divided by something that's non-zero. I'll get the y-coordinate for the center mass is going to be 0 again. We are going to find the center of mass for a system of 4 particles that are located in the 4 quadrants of a coordinate system. We have a 2 kilogram particle located at x equals positive 2, y equals positive 2. We have a 2 kilogram particle located at x equals negative 2, y equals positive 2. We have a 3 kilogram particle located at x equals negative 1, y equals negative 1. And we have a 2 kilogram particle located at x equals positive 2, y equals negative 2. For simplicity, I'm going to give these particles a label. I'll just label them 1, 2, 3, and 4 based on the quadrant that they're found in. When I find the coordinates for the center of mass of these 4 particles, I will find the x-coordinate for the center of mass separately from the y-coordinate for the center of mass. So this is essentially 2 calculations I need to do in this problem. If I look at the equation for the x-coordinate for the center of mass, I have 1 over the total mass, so I just add the masses of all the particles in my system up. And I have to multiply this 1 over m total by this summation. This summation is essentially the sum of the products of the x-coordinate and the masses of each individual particle. So for example, I would say x center mass is equal to 1 over m total. M total is the total mass of all the particles, so that would be 2 plus 2 plus 3 plus 2. 2 plus 2 plus 3 plus 2. And I multiply this by this summation. So the mass of particle 1 is 2. The x-coordinate of particle 1 is 2. The first term in my summation would be mass of 2, x-coordinate of 2. The second term in my summation would be mass of particle 2, x-coordinate of particle 2. So I would have mass of particle 2 times the x-coordinate of particle 2. Particle 2 is located here in the second quadrant. It has an x-coordinate of -2. Then I have the mass of particle 3 times the x-coordinate of particle 3 plus the mass of particle 4 times the x-coordinate of particle 4. At this point, I have a really long term with many numbers in it, but this is fairly straightforward to solve. So I could say the x-coordinate for the center of mass of this system of 4 particles is, okay, this fraction will be 1/9, and this term in brackets will be 4 minus 3 plus 4. That will be equal to 1. So I find the x-coordinate for the center of mass is 1/9. To find the y-coordinate for the center of mass of the system, I do the exact same thing, only instead of looking at the x-coordinates in this sum, I look at the y-coordinates in this sum. So the y-coordinate for the center of mass, I could write as 1/m total. We said m total is 1/9, so 1/9. And then I multiply that by the mass of particle 1 times the y-coordinate of particle 1. Mass of particle 1 is 2 kilograms. Y-coordinate of particle 1 is y equals 2. So I have 2 times 2. The mass of particle 2 is 2 kilograms. The y-coordinate of particle 2 is y equals 2 again. The mass of particle 3 is 3 kilograms. The y-coordinate of particle 3 is -1. And the mass of particle 4 is 2 kilograms. The y-coordinate of particle 2 is -2. Now I would have 2 times 2 gives me 4, plus 4 gives me 8, minus 3 gives me 5, minus 4 gives me 1. So I have the y-coordinate for the center of mass of this system of particles is 1/9 times 1, which gives me 1/9. So I could say that my center of mass for this system is located at xy equals 1/9, 1/9. At this point in this problem, we are done. We did find the x and the y coordinate for the center mass of the system of particles. However, one thing I'd like to point out, we said that if you have a figure or a system of particles that has an axis of symmetry to it, in other words, if there is a line or a way to slice between this figure or system of particles and have one half of that line be a perfect mirror image of the other half, then I expect the center of mass should lie on that axis of symmetry. So pause the video, think about it, see if you could find a line in this figure where if you were to draw a line through the system of particles, one half of that line would be a perfect mirror image of the other half of that line. The axis of symmetry in the system of particles is going to be a diagonal line that passes through the origin. If I were to draw a diagonal line that passes through the origin and look at the location of particles in this system, then the particles above the diagonal are a perfect mirror image for the particles below the diagonal if I fold along the diagonal. And therefore, I expect the center mass to lie somewhere along this axis of symmetry. And indeed, we found that the center mass is located at 1/9, 1/9, which is roughly right about there.